Okay, where was I? Oh yeah, and Lovier. And I saw this as Lenin infirmed in Hegel's lecture. But the thing I liked was that you know about this.
Sorry, Gilbert is the only man in the world who could publish a sentence like that. I get it.
Whereas it is the characterization of motion which correctly expresses the continuity of space and time. It's this part that I liked. Whereas the concept of motion as a presence of a body, one place at one time and another place at a later time, describes only the result of motion and does not contain an explanation of motion itself. That triggered something in me when I read it and thought, right, I'm going to... But then he goes on to continuously variable structures, topoi and so on. And what the hell's all this topoi business? I mean, Andrews knows all about this. But the idea of Gerard was that he said he had to, I said, sorry, I just didn't finish the story. He had some money, PhD he wanted to do. And I said, right, what do you want to do it on? He said, category theory. I said, I know nothing about category theory. How can I supervise a thesis on category theory? He said, I want to apply to quantum mechanics, and you know a lot about quantum mechanics, so I'll do you a deal. You teach me quantum mechanics, and I'll teach you category theory. So I thought this was a good deal. It was completely free. Unfortunately, we totally failed in this task. He knows very little quantum mechanics, and I know even less category theory. So, but he got his PhD. It was a very good PhD. And he did something which Mike and I were just talking about over breakfast, which is how you can use a Cartesian closed category. No, a simplicial category. Simplicial category, I beg your pardon. And actually obtain the Bose-Einstein statistical distribution. And this is either trivial or deep. And since talking to Mike and some of his contacts, I think there's something very interesting in this which has never been taken up. Anyway, and then of course I've got this triumphal statement here. That quantum mechanics is a monoidal tensor star category. I lifted that from the first time without knowing what it was.
Do we know now?
Eh?
Do we know now?
Well, Bob's going to tell us all about this, don't worry. And I found it in Sean Majid's book on quantum groups. Do you know Sean? I'm sure you do. Do you, Andres? Do you know Sean Majid? No, you don't. Okay, so he's a mathematician at Queen Mary College. I just wondered and I saw that and I thought, great, I'm going to Lou Kaufman and I'm going to say, quantum mechanics is a monoidal tensor star category. And his mouth dropped open. How do you know that? How do you know that? Okay. Now, which way do we go? No, yes, I'm going.
Whoa.
What do I do? Do I just press it? I haven't sussed this yet. Nothing's come out on here.
Diagrams. Draw them.
The pictures that were supposed to come out on that was that he had, from his category theory, this is the kindergarten category, so you can do it all in terms of pictures, that's why I call it kindergarten category theory. And he had pictures like, then he had pictures like this, and so on. And these are bras, these are cats, these are matrices, and these are Bell states. And I was just absolutely...
What was the one with the upper left? What was that, you said?
This one?
The square one, yes?
This is just a matrix. It's part of Jones's linear, planar algebra structures. And for me, this was a real turn-on signal. Because I've already drawn this twice for you in the previous book. But then this tied up with left and right ideal structure that I've been talking about, which I'm going to talk about a little bit. Just press.
What's a Bell state?
Sorry?
What is a Bell state?
This thing here. I mean, look, I'm not going to tell you what Bob's going to talk about. Sorry, I'm not going to take Bob's lecture. Sorry, what did you let me in on it?
He asked for the Bell state.
Oh, what it is. Oh, it's where it's, oh golly, it's the whole key to the quantum teleportation.
Ah,
It's when you measure, you remember quantum teleportation where you send a couple of particles away with in an entangled state.
yeah.
You then bring another particle up to this one here, and then you do a special measurement, which is called a Bell measurement, to throw this into one of these Bell states. And that immediately you find that the other particle, which is miles away right now, is in one of the states of this particle that you brought up. So that if you know what, if you send a bit of classical information, you can actually find out what this particle was that you brought up. And this is all done in the entanglement relation. It's done instantaneously, non-local, and so on. But it's to do with quantum teleportation. But Bob, I'm sure, will tell us about this. Okay, so then the question is, we really need a new order. If you think about the classical tradition of physics, locality, continuity, and determinism, we used to call that the Cartesian order. And what we've done with the Schrödinger equation is to keep it in the Cartesian order. And then we get into a rectangle mess of what everything means. And the Cartesian order, essentially, it's using tensor calculus, because you separate. When you go to Clifford algebras, you see one of the reasons why Gibbs originally, I don't know whether you know this, Ernst, originally rejected Clifford algebras, was Clifford algebras actually take a little bit of a vector and put it into a bivector. In other words, it mixes those things up under the automorphism. And Gibbs said that's not what happens in physics. But of course Dirac then finds Clifford algebras, and that's exactly what it's doing. So quantum mechanics is somehow not keeping these as separate entities. Okay, but you need one more thing which I want to bring in, and that is that the Schrödinger equation is essentially Huygens construction. I was talking to you about it. Essentially Huygens construction. So you've got a sort of Green's function approach, giving you information from all this wave surface onto the point. And Bohm wanted one more bit of new feature. I don't like this thing. One more bit of information, which is also an expanding wave. And to try and put those two things together. And to see, roughly, for people who like visual images, there's this very nice image. Because what I'm moving on to is the implicate order, where you've got two cylinders with a glycerine in between, and you've put a spot of dye in that glycerine, and then when you wind it up, the spot of dye disappears. But the amazing thing is, if it's done in the right conditions, as you unwind, the spot reappears again. So that although it looks as if you've lost the order is there, it's implicit in the glycerine, and you can make it explicate again by unfolding. So you have this image of a particle as something in the implicate order, something in the explicate order, it unfolds into the implicate order, and then